Hello friends, welcome to my YouTube channel. Friends, today we are going to discuss the design procedure for helical compression spring. It is also known as closely coiled helical compression spring, CCHS. So we are going to discuss the design procedure of this helical compression spring. Now first of all, let us see what we need to required in the design procedure of helical compression spring. We have to calculate the diameter of the wire of the spring. Okay, so if this is the spring, then we have to calculate the diameter of the wire of which the spring is made, and we have to determine the pitch of the spring, that is the distance between the consecutive coils we have to calculate, and we have to find out the mean coil diameter, that is the mean coil diameter of each coil we have to determine, denoted by capital D here. So we have to find out these things. Also we have to find out the free length of the spring. Okay, so we have to calculate this thing also, and also we have to find out the spring constant, that is the value of K, where K denote the spring constant or spring rate. Okay, so all these things we will calculate in this lecture, so keep watching the video. Now friends, generally, the maximum force which is acting over the spring is given to us in the problem. If this is the spring, so the maximum force P will be given to us, which will be acting over this closely coiled helical compression spring. Okay, and here it is given as 1252. Okay, we are discussing the given data first. So maximum force will be given to us, which will be acting on the spring in axial direction. Okay, and the ultimate tensile strength of the material will be given for the spring, and the modulus of rigidity denoted by capital G will be given to us. Okay, here in question they have given us the material as patented and cold drawn steel wire. Okay, so for that we have these properties, that the ultimate tensile strength and the modulus of rigidity is given to us. Now deflection of the spring corresponding to maximum deflection, maximum force, that is the deflection of the spring corresponding to this maximum force, is also given to us as 30 mm. Okay, so we have to design the spring based on the given information. So we will follow a step-by-step procedure, and let's follow that procedure so that you will be able to design the spring very easily. So first thing is the assumption of the spring material. So we have to first assume the spring material. Now here patented and cold drawn steel wire is given as the spring material. Suppose it is given here, but suppose the material is not given to us, then you can assume the material according to your application, and the various materials which are used for construction of the spring are given here. Patented and cold drawn steel wire can be used for material of the spring. Also oil hardened and tempered steel wire can be used. Oil hardened and tempered steel can be used. Stainless steel spring wire can also be used, and their property can be available can be taken from the design data book, that is the ultimate tensile strength we have to require and the modulus of rigidity. But here in problem, patented and cold drawn steel wire is given to us, so we will use the properties of this patented and cold drawn steel wire, ultimate tensile strength and modulus of the rigidity, which are this much and this much. Okay, so first step is the material selection. So we have selected our material and write down the properties of that material, the ultimate tensile strength and the modulus of rigidity. Now the second step, we have to calculate the permissible value of shear stress for steel. Now the permissible value of stress for steel for spring wire is taken as tau permissible is equal to 0.5 times the ultimate tensile strength. Okay, so ultimate tensile strength is given to us as 1089. 1089 is given in the question, so we can put here 1089 and find the value of permissible shear stress as 544.5 Newton per mm square. Now go to step number 3. Now in step number 3, we have to choose the value of the spring index, that is we have to assume a suitable value of the spring index. The spring index we have already known, or we have already studied, that it is the ratio of the mean coil diameter to the diameter of the spring wire, that is capital D divided by small d. Now the value of CS, that is the spring index, generally taken between 6 to 10, but for most of the engineering applications the value of the spring index lies between 8 to 10. But here we can take it as 6. So I am assuming the value of the spring index as 6 because we can assume the value of spring index between 6 to 10. So I am taking spring index Cs as 6. Now the next step is the Vols factor calculation. So let us see how we will calculate the Vols factor. Now the Vols factor is noted by K. It is given in all design data book. The formula of Vols factor is 4Cs minus 1 divided by 4Cs minus 4. So we have assumed the value of Cs in step number 3 as 6. Now we will put this value of Cs in this formula. After putting the value of Cs as 6 here, here and here in place of Cs, we can obtain the value of Vols factor as 1.252. Okay. So we have calculated the value of Vols factor. Now the next step we have to look. In the next step, using this Vols factor and the resultant shear stress equation for the spring wire case, we have to calculate the diameter of the spring wire. So resultant shear stress in case of spring wire is tau s, denoted by tau s, is given using this formula, where tau s is equal to K, where K is the Vols factor, 8P, P is the maximum force acting on the spring, and CS is the spring index, and pi d square, where d is the diameter of the spring wire. We all know the value of tau s from the step number 2. We have already calculated the value of tau permissible in the step number 2 as 544.5 Newton per mm square. So we will put the value of tau s as 544.5 Newton per mm square here, and the value of K we have already calculated in the step number 4. The value of K is 1.252. So we will put the value of K as 1.252 here, and P is already given in the question as 1252 Newton, that is the maximum force is given as 1252 Newton here, and CS is 6 assumed in the step number 3 of the problem. We have already assumed the value of CS as 6, and the diameter can be calculated using this equation by solving this equation. When we solve this equation, we have find out the value of the diameter as 6.6, nearly equal to 7 mm. So we will take the value of diameter of the spring wire as 7 mm. Okay, now go to step number 6. In the step number 6, we have to calculate the mean coil diameter of the spring. Okay, the mean coil diameter, that is the diameter of the coil of the spring, we have to calculate. So using the value of the spring index, that d, the diameter of the mean coil diameter d is given as spring index into diameter of the spring wire. So spring index is 6. We have already assumed the value of 6 in step number 3. Spring index as 6 in the step number 3, and the value of diameter of the wire is 7 mm, calculated in the step number 5. So we can calculate is the diameter of the mean coil diameter of the spring, capital D, as 42 mm. Now let us come to the step number 7. In step number 7, number of active coils we have to calculate. Number of active coils means that the coils which are taking part in the compression and extension, okay, that are called as the active coils. So the number of active coils is equal to delta is equal to 8P, where P is the force, maximum force, D is the capital is the mean coil diameter, and N is the number of active turns, divided by GD raised to power 4. Okay, where D is the diameter of the wire, and G is the modulus of rigidity. So we all know all these values we know because delta is given as 30 mm here. Deflection of the spring corresponding to maximum force is given as 30 mm. So take this value from there. The 30 mm is taken from there, and P is given to us as 1252 Newton. That is the maximum force is given to us as 1252 Newton. And D we have already calculated as 42 mm. Here D will put the value of capital D as 42 mm here, and the value of N we have to calculate, and G is given to us in the question as 81369, and D, capital small d, we have already calculated in the step number 5 as 7 mm. So we will put all these values and solve for the value of N. So the total number of active coil will come out to be nearly equal to 8 coils. Okay, now go to the step number 8. In the step number 8, we will find out the total number of coils. Okay, so we will calculate the total number of coils. We in the previous step we have calculated the number of active coils, but the total number of coils will be greater than the number of active coils. So we will calculate here the total number of coils calculation, that is NT. Now in the step number 8, we will go to the design data book and search for this table. In this table, you can find out the various styles of the spring and total number of active turns in that spring. The active turns in that spring denoted by N using this form, these table. So suppose I am choosing you can choose any of the style of the end. I am choosing square end, and for square end, active turn denoted by N is given as NT minus 2, where NT is the total number of turns and N is the total number of active turns. Okay, so from here, corresponding to the square ends, I will take the spring, the number of active turns as NT minus 2. So the total number of turn NT is equal to N plus 2. Okay, using this table. Okay, using this table for square ends. So NT, the total number of turn is given as N plus 2 and N is given as 8. Sorry, calculated as 8. So putting the value of N as 8, capital N is 8, we will get the value of total number of coils, which is 10. Now, calculate in the step number 9, we will calculate the free length of the spring. Okay, so we have to calculate here the free length of the spring. Now, free length is given as the sum of solid length, that is when there is no gap between the spring wires, that is spring is fully compressed, and plus total axial gap between the consecutive coil, that is between the consecutive coil there will be a gap, there is gap between the consecutive coils, so the sum of that gap we will add to this, and the deflection delta, that is the deflection of the spring because of a force acting on the spring, we have to take here. Now the free length is given, solid length is given at NT, that is this NT into D, D is the diameter of the spring wire, and plus 1 into NT minus 1, that is the total axial gap between the consecutive coil is taken as 1 into NT minus 1, where 1 is the gap between the single consecutive coil, that is here we have assumed that you have to assume that the gap between two consecutive coils is 1 mm. Okay, so you have to use this as 1 mm. Assume this as 1 mm and NT minus 1. NT we have already calculated, and 30 is the deflection which is given us in the question. Okay, maximum deflection. So we can find out the value of free length of the spring. After that, we will calculate the pitch of the coil. So the pitch of the coil is given as free length divided by NT minus 1. Free length will come out from here, and NT is 10 here. We have already calculated NT as 10, so we can calculate the pitch from here, and the spring rate we can calculate using this formula as GD raised to power 4 8 DQN is equal to K, where K denotes the spring index. Here this K denotes the spring index, or K denotes the spring rate. Okay, so G given to us in the question as 81369, and D we have calculated in the step number 5 as 7, and DQ we have calculated in the step number 6. This D we have calculated in the step number 6 as 42, and N we have already calculated in the step number 7. So we can calculate the value of the spring rate. So this was all for today's topic, friends, and if you like my video, you can subscribe to my channel and also press the bell icon for the notification of the upcoming videos. So thank you, friends, for watching the video.